In this video, we're going to look at how PLA is synthesized from renewable resources, some possible uses, and how it's dealt with at the end of its life. So, is PLA the future of sustainability? Growing awareness for how our actions are affecting the planet, consumer preferences on sustainable products, whether that's how they're processed or packaged, are forcing manufacturers to change common practices to attract and keep business. This is highlighted in the 2015 Global Sustainable Development Report. One substitution that manufacturers could make is swapping to PLA plastic, short for polylactic acid. This can be manufactured from renewable resources, so hopefully we'll come back to this point, and a reliance on fossil fuels and feedstock. Go plants! PLA uses a feedstock of corn, sugar beet or cane, and potatoes. The feedstock obviously changing depending on the climate and availability in the region, with corn being the primary feedstock in the US. The feedstock is ground into mulch and fermented in bacteria at about 40 degrees Celsius in a pH range of 5.4 to 6.4. Firstly, glucose is catalysed by ATP energy transfer from the bacteria, forming two Pyruvate ions. These two Pyruvate ions then undergo lactate fermentation, where two NADH molecules from the bacteria cells and protons from the slightly acidic environment convert the molecules into lactate ions, then into lactic acid once protonated. There are many complicated intermediate steps, however, to concentrate on the focus of this video, I'll leave it here. Now we have our monomer and can begin polymerization. PLA is synthesized through a ring opening polymerization of lactide, which is a cyclic dimer of lactate. This is done by the polymerization of short, low molecular weight pre-polymers of PLA, and then into lactide rings. The lactide rings are then polymerized into large PLA polymers, which can be used for many applications. Once synthesized, PLA can easily be processed through melt processing, where PLA resin chips are heated above its melting point of 180 to 200 degrees Celsius, depending on the chain length. This means it can easily be made into different products and behaves like many other plastics used today. PLA can be cast into components, injection stretch blown into bottles, as shown, or cast and extruded into films and sheets. Furthermore, PLA has a great benefit of being clear, so it's ideal for single-use packaging. Being made from renewable resources isn't the only pro for PLA. Like traditional plastics, PLA can be recycled, but also industrially composted. During this process, the waste can take up to 12 weeks at 57 degrees Celsius to completely compost. Although this is better than incinerating or putting into landfill, recycling or reusing the waste has the smallest environmental impact. However, as classified by the European Union, PLA is only classified as biodegradable and not compostable, meaning it will take a very long time to break down if not treated in the proper conditions. When PLA is exposed to water, hydrolysis occurs and the ester groups are cleaved, decreasing chain length and strength. Firstly, a hydroxide ion deprotonates an OH group on the chain. This negative oxygen atom then bonds to the carbon of a C double bond O of a different ester group, and the electrons are rearranged. Now a ring is formed, electrons are rearranged once again, and the carbon-oxygen bond is broken or cleaved. Dehydration of the lactide produces lactyl lactic acid, taking us back to our original starting monomer of lactic acid. The process can also follow via an acidic route, where an OH is protonated, forming a ring intermediate, allowing water to attack the carbon-oxygen bond, and once again, the ester bond is cleaved. Both reactions are self-catalyzing, with both reactions producing hydroxide ions or protons. The polymer can also undergo photodegradation. One way is by the breakage of the main chain carbon-oxygen bonds. The UV energy homolytically splits the carbon-oxygen bond, producing two radicals. These radicals then react with other chains, ripping off hydrogen atoms. The other forms hydroperoxide derivatives. Then, with further degradation, carboxylic acid and diketones are formed. Now, Finally, before we can answer the question on whether this up-and-coming polymer is going to solve all our problems, we need to look into the ethics of the life cycle. The use of land to grow virgin crops for feedstock is something that concerns many people, and they're right to be. With only 5% of the global harvest currently being grown for fuel or feedstock, demand will put a strain on global food supply chains, in addition to accelerating deforestation and habitat loss. These negatives do not outweigh the possible benefits gained. In conclusion, although PLA might be the solution to fixing some areas of the industry where plastics are necessary, the only true way of tackling climate change is to change people's habits by moving away from the use of single-use plastic and throwaway culture.